Hello. As I was standing here and preparing for today's lecture, I thought of a very funny story. So once a general sent some of his soldiers for excavation. He called them up and asked, how many of you guys went? The reply came, 3. The general asked his soldiers to send half of them back. The soldiers were thinking how to divide 3 into half and get 3 by 2 soldiers back. I know this is not that funny. So let's keep it aside and launch our today's topic. Even before starting today's topic, let us think that dividing 3 persons into half is not possible. But on the other case, if you were asked to divide 3 inches into half, that made significance. So let us launch what is today's topic, that is complex number. Now, going back again to my initial story, that is dividing 3 persons into half, that was not making significance. So, let us get into the origin of our number system. So, initially what we had was just integral number system, in which all the numbers were in the form of integers 1, 2, 3, that is all the integral numbers used to exist. In that case, an equation of 2x plus equals to 3 used to make sense because here 2 is an integer, 3 is an integer. When we had to solve this equation, what we used to get was x equals to 3 by 2. But in integral number system, there was no number defined as 3 by 2. So what would be the solution of this type of equation? If it is in the case of integral number system, what I will say is this equation does not possess any solution. But if I need to define a value for x, what I'll have to do, I'll have to invent a new number system, that is rational number system that exists right now. But the question is there a need to develop a new number system and get the value of x? That is it necessary that this equation should have a solution or not? Now, referring back to my previous example, if I say x represents the number of soldiers in this case, then x equals to 3 by 2 does not make sense because a number of persons can always be integral. Contrary, if this x in this case would be representing number of inches or any length in meters or anything or something of that sort, then I will say this equation may possess a solution because in that case 3 by 2 makes sense. So, in order for this equation to possess a solution, we developed a new number system known as real numbers. Now, what I defined here was a real number is a system of numbers or a set of numbers x such that x square would be always greater than or equals to 0. So, in order to possess this equation this equation should have a solution, what we led to is we developed a new number system, that is real number system. Now this real number system even included the integral number system and all the properties that the integral number system used to hold were even valid in the real number systems. Now in real number system, I say let us take an equation which is of the form x square equals to minus 1. Now, in case of real numbers, this equation does not possess a solution because as per the definition of real numbers, x square should always be greater than 0. Now, in order for this equation to possess a solution, what we have to do is we have to define a new set of numbers so that even this equation could possess a solution. But the question is whether this equation should have a solution or not. If we need this equation to have a solution, then only we will develop a new number system. Otherwise, there is no need. Now, in order to get the requirement of this equation to possess a solution, let us take an example of an exponential system, equation of the form y equals to e to the power rx. When I differentiate y, what I get is y dash equals to r into e to the power rx. Similarly, y double dash would be r square into e to the power rx. So what is happening is with every differentiation, 1 r is coming here and e to the power rx is still remaining. So y to the power n, y prime n would be r to the power n into e to the power rx. Now the question, why I am using this exponential equation? Usually I use such type of equation to solve any equation of the form y double dash plus y equals to 0. Here y is double differentiation of y with respect to x, that is d square y by dx. Now, why I have considered this equation only? One of the reasons for considering this equation is that I really know the solution of this equation. For example, if I apply geometrical functions like sin x here, I know d square by dx of sin x is minus sin x and y is sin x. So what I am going to get here is 0. And similarly, y double prime of cos x is minus cos x. So this is minus cos x plus cos x is even equals to 0. So now I know that this equation possesses at least 2 real roots of the form sin x and cos x. Not only this does this equation possess a real root, this equation even has a physical inference. What I know from what I get from this equation is y double dash is equals to minus y. That is, double differentiation of a function is equals to the function. Can I say if y is equals to the displacement, then y double dash is acceleration? So what I am getting from here is acceleration equals to minus of displacement, which is the equation for simple, which is nothing but the equation for simple harmonic motion. So what I get, so now what I know is that this equation has at least 2 real roots of the form sin x and cos x, and not only that this equation mechanically has roots, it even has a physical inference of in terms of the equation for simple harmonic motion. Now let us put y equals to e to the power rx in this equation. So what I get here is r square e to the power rx plus e to the power rx equals to 0. I am taking e to the power rx common. So what I have is r square plus 1 equals to 0. Now e to the power rx cannot be equal to 0. So I will say r square plus 1 has to be 0. This implies r square is equals to minus 1, or r is equals to plus minus under root of minus 1. Now there is no number of the form minus 1 that exists in our real number system. So let us invent a new number and call iota, new number iota, and let us say iota is equals to under root of minus 1. Now what I can say is r equals to plus minus iota, and the equation that we were solving was y is equals to e to the power rx. So now I can say that y has this equation has 2 solutions, which are e to the power iota x and e to the power minus iota x. This is what we have derived mechanically by putting e to the power rx in this equation. But I already know that this equation has 2 solutions, which are cos x and sin x. So these are the two solutions of the equation which I know that exist, and these are the two solutions which I have derived mechanically. So one thing is, that is what very sure is, that this equation does possess a solution, and the two solutions that came out were e to the power ix and e to the power minus ix, and what we already know that exists are cos x and sin x. So somewhere or the other place, I feel I have a great gut feeling that iota does exist, and somewhere that e to the power ix and e to the power minus ix is somewhere or the other place related to cos x and sin x. So I can say that the so-called number iota, which I say is an imaginary number, is not imaginary but does have a real existence and would be used to solve a lot of mechanical problems or problems related to the physical world. So I'll say that this imaginary number iota not only adds value to mathematics, but is even used to solve lots of problem of physical world application. So now what we have studied now is that in order to get solution of the equations of the form 2x plus 3, what we required, we had to develop a new number system, that is the real number system, so that this equation may possess solution, and we wanted this equation to possess solution because this makes significance. Similarly, for this equation, that is x square plus minus 1, to possess solution, we will have to develop a new number system the way we invented real number system. So now let us introduce a new number system so that even this equation does possess a solution. So now I am introducing a new number system called complex number, and I say a number z with any number z which is of the form x plus iota y is said to be represents a complex number where x and y are real parts. Again, I am repeating once again. Now we are introducing a new number system called complex number system, and any number which can be represented in the form of x plus iota y would be called a complex number. Now where I will say x and y are real numbers. Now what we saw initially was when we extended integral number system and formed a number system, a real number system, then the real number system even composed integral number system. Now we are extending real numbers to form a new number system of complex number. So our complex number should even compose real numbers. Now seeing the definition of complex number, what I say z equals to x plus iota y. Now if I put y equals to 0 in this equation, then the imaginary part goes away. So what we are left with is z equals to x, and we have already said that x is a real number. So we know that this new number system, that is complex number, even composes of real number. Now what we have defined till now is a set of number. But every number system composes of not just a set of numbers but also the rules that can be applied on that set, so that we can perform operations on that set of number. Plus we can combine these sets of number to form a new number. So let us define some structure structures for complex numbers. I say two complex number. First, I say two complex number would be equal if and only if their real part, their real component and their imaginary component are equal. Before even telling what is the defining the equality, let us first understand what is the real component of a complex number and what is the imaginary component of a complex number. So for this complex number, z equals to x plus iota y, x is said to be the real coefficient of complex number and is denoted by real of z, and y which comes with which is associated with iota, that is which is the coefficient of the imaginary part, is said to be the imaginary part of complex number and is denoted by imaginary of z. So what I get now, let us define the equality of complex numbers. So I say two complex numbers are equal if and only if their corresponding imaginary and real parts are equal. So let's say z1 equals to x1 plus iota y1 and z2 equals to x2 plus iota y2. Then we will say z1 would be equal to z2 if and only if x1 is equals to x2 and y1 is equals to y2. Second, the way we have defined equality, let us even define addition for two complex numbers. So I will say, considering the same number z1 and z2, I will say z1 plus z2 would be equal to, now what we are doing is, we are adding the imaginary components and we are adding the real component separately and the imaginary component separately. So what I get here is x1 plus x2 plus iota y1 plus y2. Let us define one more structure. I say when a complex number is multiplied by a real number, so that is when I multiply a real number r with my complex number z, which is of the form x plus iota y, what I get is rx plus ry, r iota ry. That is the real part, that is the real number is multiplied with the real component and it is again multiplied with the imaginary component. That is, we have defined till now we have defined three structures for complex number. The first is related to the equality of two complex number. The second one is related to the addition of two complex number, and the third one is related to the multiplication of complex number with the real number. Now don't you think after defining these three structures for a complex number, we have defined complex number as a two-dimensional vector? That is the way we can represent real numbers on a plane. Similarly, we can even represent complex number on a plane. Now, let us consider any real number r equals to x, or let's say r equals to 4 or 5. We do not need to imagine these numbers pictorially, but we can easily represent them on a number line. That is, x-axis is just a convenient way to represent them. Similarly, this complex number of the form x plus iota y is a two-dimensional vector in which x is the real part, y is the real part, and they both are independent of each other. So I can even represent them on a two-dimensional plane. So let's draw this plane. I have the number z here, which is of the form x comma y. This is my x-axis, which is going to represent the real part of x. So I can even define it as real axis. And this is my y-axis, which is going to represent the imaginary part of z. So what I can say, I can even say it to be imaginary axis. Let us join origin and z. Now this distance is going to be x and this distance is going to be y. When I join O and Z, what I am getting is a vector OZ which is going to make an angle theta with the x-axis. Now what I am trying to convert these Cartesian coordinates xy in form of polar coordinate r comma theta. So let us define this length to be r. So I can say x is going to be equal to r cos theta and y is going to be equal to r sin theta. Thus, I can even represent this complex number z x comma y in terms of polar coordinate r comma theta. But one thing that is very important and has to be taken into consideration is when we define complex number in terms of polar coordinate, then this r, which is this distance, which can be defined as under root of x square plus y square, is always going to be positive. In the Cartesian, in terms of real numbers, when we used to represent real numbers in polar coordinates, we could have this r to be positive or negative. But in terms of complex number, this r is always going to be positive only. So when we try to understand this, when we try to analyze this, what we get is this r is nothing but the displacement of the complex number from the origin. Now we have developed a background for complex number where we have defined any complex number where we define that any complex number would be in the form of x plus iota y, and this complex number is the extension of the real number. So this complex number would even consist of real numbers. Even when we see the geometrical representation in this 2D plane, one more thing, this 2D plane is said to be Argand plane, and this representation of complex number on Argand plane is defined as Argand diagram. Here this distance OZ, that is the displacement of Z from the origin, is even denoted by mod Z, which is equals to under root of x square plus y square, and this is termed as modulus of Z, and this angle theta is said to be as argument of Z. Let's not confuse this argument with this argument of ARG this ARG of the Argand diagram. This is just a funny coincidence. This ARG represents argument of Z. So now coming back to the initial discussion that we continued. So we have developed a background for complex number. We have even defined structure for complex number, and we have even seen this. We can represent this complex number Z on a two-dimensional plane, this two-dimensional plane is said to be Argand plane, and this representation of complex number on Argand plane is termed as Argand diagram. We can represent this complex number Z in form of polar coordinate r comma theta, where theta is always going to where r is always going to be positive. One more thing, we have defined equality of two complex numbers, but we cannot define order of two complex number. That is, if I say I have two complex number Z1 equals to x1 plus iota y1 and z2 equals to x2 plus iota y2, then I can never say that z1 is greater than z2 or z1 is less than z2, the way we used to define it in real numbers, but we cannot define this in terms of complex numbers. This is just a small note to make. Now let us try to apply these structures that we have defined on complex number, so that we can understand this a bit more better. I say z1 equals to, let us assume z1 equals to 2 plus iota 3. So in this case, the real part of z1 is 2 and its imaginary part is 3. And say z2 equals to 4 plus iota 5. Then here the real part of z2 is 4 and its imaginary part is nothing but 5. So I have to show, is z1 equals to z2? No, because the real part is not equal to the real part of z2 and the real part of z1 is not equal to real part of z2. I say one more complex number, z3 equals to 2 plus iota 3. Now in this case the real part of z1 is equal to the real part of z3 and the imaginary part of z1 is equal to the imaginary part of z3. Thus z1 is equals to z3. Now what I have to find is z1 plus z2. z1 plus z2. So what I have to do is add their real parts. So what I will do is add 2 plus 4, that is 6, and add their corresponding imaginary part, that is 3 plus 5. What I get here is 8. Now I have to find 4 into z1, that is I am multiplying 4 with 2 plus iota 3. Now what we had defined was, when we multiply a real number with a complex number, we are going to multiply the real part with the real component and the real number with the imaginary component. So what we are doing here is 4 into 2, that is 8, plus 4 into 3, that is iota 12. Let us try and define some more additional structures for complex number. So let us start by defining what is z1 into z2. One thing that we should take into consideration while defining z1, z2 or z1 plus z2 or any other mathematical operation on this complex number is that when this complex number consists of just a real number, that is when the imaginary part of it is 0, then even this result should hold valid and should be equal to what we used to get while multiplying just two complex numbers. Otherwise it is really going to be hilarious when we say that when we consider a real number as complex number and multiply them, we get a different result, and when you multiply them considering as two real number, we get a different term. So what I want to convey is that this multiplication or any operation on complex number has to be in parallel with the operations on real number. So let us define what is z1 into z2. Let this be a1 plus iota b1 and a2 plus iota b2. I am multiplying it in the same way, the way we used to multiply in case of real numbers. So I will multiply a1 with a2, a1 with b2, b1 with a2, and this with this. So what I am going to get here is a1 a2 plus a1 iota into a1 b2 plus iota into b1 a2 minus plus iota square b1 b2. Now just to refresh our memory, we have defined iota as root of -1. This implies I square is going to be -1. So I can safely put this I square equals to -1. So what I get here is A1 A2 minus B1 B2 plus iota of A1 B2 plus B2 A1. A1 B2 plus A2 B1. So this is how we multiply two complex number. Now what I said initially was this multiplication has to be in parallel with the real number multiplication. That is, when these complex numbers Z1 and Z2 turns out to be two real number, even then this result should apply. This result should be valid. Let us see how this is going to be. So when Z1 turns out to be a real number, then this imaginary part is not going to exist. So I'll say B1 would be equal to 0. And when Z2 turns out to be a real number, then this part B2 is going to be 0. So when in this equation B1 and B2 turns out to be 0, what we are left is A1 A2. This is going to be 0 as B1 B2 are 0, B2 0, B1 0. What I am going to left it with is just A1 and A2. That is the multiplication of two real numbers A1 and A2. So this result is in parallel. So is in parallel with the rule for the multiplication of real numbers. Let us even see how we divide two complex numbers. Now since we have understood the multiplication of complex number, the division is going to be really easy. I say Z1 divided by Z2. Now no, this is nothing but multiplication of Z1 by 1 by Z2. And this is very easy. Now you guys can do it yourself even. You have to do nothing but just substitute Z1 by A1 plus iota B1 and this by 1 upon A2 plus iota B2. Now the easier way to solve this would be to rationalize the denominator. So what I am doing is I am multiplying A2 minus iota B2 in the numerator and denominator. So what I get here is A1 plus iota B1 into A2 minus iota B2 upon A2 plus iota B2 into A2 minus iota B2. This is nothing. Now multiplying the similar rules of multiplication, what I am going to do is multiply A1 by A2, A1 by B2, this by this and this by this. So what I get here is A1 A2 minus iota A1 B2 plus iota B1 A2 and minus iota square B1 B2. Now isn't this in the form of x plus y and x minus y? So in real numbers we used to say that x plus y into x minus y is nothing but x square minus y square. So I am applying the similar rule here and writing this as A2 square minus iota P2 square. What this turns out to be is A1 A2 plus B1 B2 plus iota B1 A2 minus A1 B2 upon A square plus B square upon A2 square plus B2 square. This is how we define division of two complex number. Now let us consider one special case of the multiplication of two complex number, which we have already discussed here. If I take two complex number of the form a plus iota b and multiply it with another complex number of the form a minus iota b, what I am going to get here is, let us multiply and see. A into a minus iota ab plus iota ab minus iota square b square. This is nothing but equals to a square plus b square, which is nothing but equals to modulus of z whole square. So if I try to understand this geometrically, or where z would be equal to modulus of a plus iota b whole square. So if I try to understand this geometrically, this is nothing but the distance of the complex square of the distance of the complex number z from the origin, or the displacement of z from the origin. Now let us go back from where we started defining the complex number, and we invented a new number iota, which would be equals to minus 1. Now let us try to see some special properties of this number iota. So when I try to square this number iota, what I get is square of under root minus 1, which is nothing but equals to minus 1. Similarly, when I try to take cube of this number, what I get, I can write this cube as iota square into iota, which is nothing. I know iota square is minus 1, so I can put minus 1 here. What I get is minus iota. Iota to the power 4 is nothing, can be written as iota square into iota square, that is minus 1 into minus 1, which is equals to 1. Let us see what is iota to the power 5. This can be written as iota power 4 into iota. Iota to the power 4 is 1. What I get here is iota. This seems to be seem to follow a pattern, that is iota to the power 1 is minus under root of minus 1, iota square is minus 1, iota cube is minus iota, iota to the power 4 is 1, 5 is again iota, then iota to the power 6 is going to be minus 1, to the power 7 equals to minus iota, and to the power 8 equals to again 1. Let us try to generalize this result. So I can say iota to the power 4n would be equal to, can be written as iota to the power 4 into n. We already know iota to the power 4 is 1 and 1 to the power n is 1. So this is nothing but equals to 1 always. So I can say iota to the power 4n is always going to be equal to 1. Similarly, if I say iota to the power 4n plus 1, this would be equal to iota to the power 4n into iota. Iota to the power 4n is 1. So this turns out to be iota. Now what I have is iota to the power 4n plus 2. Iota to the power 4n is 1 into iota square. Iota square is minus 1. So what I get here is minus 1. What I get now, what I define is iota to the power 4n plus 3. Iota to the power 4n is 1 again. Iota cube is minus iota. So what I get here is minus iota. So this way we can find any power of iota. Let us say I want to find iota to the power 40008. Can you guys try this? This seems out to be a very big one. I don't know how many times I have to multiply iota item. But what I see is this 4008 is a multiple of 4. So I can define it as in the form of iota to the power 4n. This is going to be equal to 1. Similarly, we can find any power of iota. For example, let's say I want to find iota to the power 57. I can write it as iota to the power 56 plus 1. 56 is a multiple of 4. So what I get here is iota. Similarly, we can even define negative powers of iota. For example, I want to find what is iota to the power minus 1. I can write this as 1 upon iota. This would be equal to, I am multiplying iota in numerator and denominator. So what I am getting here is iota upon iota square. Iota square is minus 1. So this turns out to be nothing but equals to minus iota. Similarly, we can define anything. For example, like iota to the power minus 13, which would be equal to nothing. We can define as 1 upon iota to the power 13. Iota to the power 13 is going to be equals to 1 upon iota, that is iota 12 into iota. Iota to the power 12 would be equal to 1, 4n of the form 4n, and this is equals to minus iota. This way, we just have to remember these 4 generalized equations of the powers of iota, and we can find any power of iota.